The hottest place in the universe is not the Sun. It is not a star, not a supernova, and not even the glowing edge of a black hole. The real answer is far stranger, far smaller, and far more extreme than it first seems. Tonight, this journey moves from the cold darkness between galaxies to the deepest confirmed heat science has ever found. If this kind of cosmic exploration belongs here, please like the video, subscribe to the channel, and settle in for the true hottest place in the universe. At the widest scale, the universe presents itself first as darkness. Space between the great structures appears empty, calm, and almost without character. Yet even this apparent emptiness has temperature. Astronomers describe temperature as a measure of average energy in matter or radiation. In daily life, temperature is felt through skin, air, water, stone, and flame. In astronomy, it is read through light. Every region of the cosmos leaves some trace in the form of radiation, and that radiation carries information about heat. The coldest broad background of the universe glows in microwaves and fills all directions almost evenly. A faint remnant from the early cosmos that now sits only a little above absolute zero. It is not visible to human eyes, yet it is everywhere, and it gives the broadest thermal backdrop against which all hotter places are judged. From that nearly uniform background, the temperature map of the cosmos begins to spread outward into contrast. There are dark regions colder than most stars and bright regions hotter than most matter found on planets. Clouds of gas drift through galaxies at low temperatures by cosmic standards. Dust grains absorb starlight and warm gently. Planets receive heat from nearby stars and radiate it away. Stars themselves hold bright surfaces that range from a few thousand degrees to many tens of thousands of degrees. Some stellar cores rise vastly higher than their surfaces. Then there are violent places where gravity, collapse, shock, and collision push matter into states that ordinary language barely captures. The universe is not hot in one simple way. It contains many kinds of heat, spread across many kinds of environments. The first task is to understand how this range is compared without losing the scale of the whole. Astronomers do not usually travel to these places. They measure heat from afar. A cool object gives off longer wavelength of light, often infrared or microwave radiation. A hotter object shifts toward visible light, ultraviolet light, or X-rays. Extremely hot matter can emit X-rays strongly, and the most energetic processes can also produce gamma rays. This does not mean that every X-ray source is the hottest place in existence. It means that X-rays are often signs of gas heated to millions of degrees. In the same way, visible starlight does not mean a star is modest in temperature. It means its surface radiates in a range that human eyes can detect. The universe therefore requires a careful reading. A dim source may be extremely hot. A brilliant source may be cooler than something almost invisible. Heat in astronomy is not judged by brightness alone, but by the character of the light and the physical process that produces it. This wide cosmic view also requires a distinction between a place and a moment. Some regions stay hot for very long spans of time. Giant reservoirs of gas in galaxy clusters can remain at tens of millions of degrees, held by gravity on scales larger than individual galaxies. Other conditions are brief and violent. A small volume of matter can become much hotter than a galaxy cluster, but only for a tiny fraction of a second. When people ask for the hottest place in the universe, the answer depends on whether the question refers to long-lasting natural environments, brief natural events, or the hottest matter ever produced and measured directly. Science keeps these categories separate because they describe different realities. a cluster of galaxies, the surface of a star, the inner flow around a black hole, and a laboratory collision at a particle accelerator all belong to different thermal worlds. Each must be understood on its own terms before any ranking becomes meaningful. At the broadest outer level, the cold background remains the most stable reference. It surrounds galaxies, passes through intergalactic space, and marks the low thermal floor of the present universe. Against that floor, the common material of galaxies already appears warm. Gas between stars may be very cold in dense molecular clouds, or much hotter in diffuse regions shaped by starlight and shock waves. Stars then rise above that galactic medium as local furnaces. Their surfaces are bright, but their inner regions are hotter still, and this difference introduces one of the central habits of astronomy. Surface appearance can hide deeper thermal layers. The same principle grows more important in more extreme objects. A place that seems calm in visible light may shelter matter at extraordinary temperatures when viewed through X-rays or through the motion of particles. The universe is layered not only in space but also in thermal depth. As the map expands further into the most energetic environments, gravity begins to dominate the story. Gravity gathers gas, compresses it, accelerates it, and turns motion into heat. In galaxy clusters, enormous amounts of falling matter and past collisions leave gas heated until it shines in X-rays. In the surroundings of black holes, matter spirals inward and can grow hotter still. In exploding stars, shock waves race through matter and produce brief extremes. In the earliest universe, all of space itself is far hotter than any ordinary structure seen today. Then, in modern laboratories, heavy atomic nuclei are collided at enormous energies to recreate a tiny sample of that early state of matter, reaching temperatures of trillions of degrees. These categories do not belong to the same scale of size or duration, but they do belong to the same physical quest. They ask how far matter can be pushed when gravity, motion, pressure, or collision drives energy into it. Observations indicate that several natural settings can claim extreme heat, depending on how the measurement is defined. Gas in large cosmic structures is measured in tens of millions of degrees. Material near the most active compact objects can be hotter. The early universe is understood to have been hotter still. It remains uncertain, in some individual astronomical cases, exactly which observed natural source deserves the title of hottest present-day place, because different methods measure different forms of temperature, and because distant objects can be difficult to model completely. By contrast, the hottest matter directly produced under controlled conditions is more secure quark-gluon plasma. The state recreated in heavy ion collisions reaches temperatures of trillions of degrees and serves as a firm benchmark for the highest temperatures ever achieved in the laboratory. This does not settle every version of the cosmic question, but it gives the temperature map a reliable upper reference point. So the outermost view settles into a simple truth. The universe is mostly cold, but not uniformly so. Against an almost frozen background, matter gathers into islands of heat. Some are gentle, like dust warmed by starlight. Some are steady, like stars. Some are immense, like the gas that fills galaxy clusters. Some are fleeting and violent beyond ordinary imagination. The search for the true hottest place begins not with a single object, but with this full temperature landscape. Only after the broad map is laid down can the hotter regions be approached one by one, each in its proper scale, each measured by the light it leaves behind, and each compared against the vast cold silence that surrounds it. Beyond the boundaries of galaxies lies a region so thin that ordinary experience offers almost no comparison. Intergalactic space contains matter, but only in scattered traces. It is not a perfect vacuum. It holds lonely atoms, faint radiation, drifting charged particles, and the broad microwave glow left from the early universe. In this outer region, temperature becomes a subtle idea. There is so little material that heat does not behave as it does in air, water, or stone. A single particle may carry energy, yet the region as a whole can still be described as extremely cold. Most of the volume of the universe belongs to this quiet realm between galaxies, and most of that volume does not burn, boil, or blaze. It remains one of the calmest thermal settings in nature. The first feature of this region is its emptiness. A galaxy contains stars, gas clouds, dust, planets, magnetic fields, and compact remnants. Between galaxies, these things almost disappear. Matter is spread so thinly that even a cubic region of vast size may contain only a small number of particles. This low density means that particles seldom collide. In dense matter, frequent collisions allow energy to spread quickly and produce the familiar warmth of ordinary substances. In intergalactic space, collisions are rare. Energy can remain tied to isolated particles or thin streams of gas without building the kind of shared warmth that fills a room or heats a surface. The result is a region where temperature must be described with care, because the usual sense of warm and cold does not fully apply. Still, astronomers can measure it. Some intergalactic gas is cool by cosmic standards, especially where it has not been strongly disturbed by nearby galaxies or large structures. Some of it is warmer because ultraviolet light from galaxies and quasars strips electrons from atoms and leaves the gas ionized, meaning that the atoms are broken into charged parts. This ionized gas may reach temperatures of thousands or even tens of thousands of degrees, which sounds intense in ordinary language. Yet because it is so thin, it does not resemble a furnace. It does not glow like a star. It drifts in near darkness, carrying energy across immense distances while remaining almost ghost-like. In this setting, a temperature can be numerically high while the environment still feels empty, diffuse, and quiet. Intergalactic space also contains a more elusive component known as the warm-hot intergalactic medium. This is a thin web of gas stretched along the large-scale structure of the universe, linking galaxies and clusters across enormous distances. It forms as gravity slowly draws matter into filaments and sheets. As gas falls into these structures, it is compressed and shocked. A shock is a sharp disturbance that moves through matter faster than the local speed of sound in that medium, forcing the gas to heat suddenly. Through this process, parts of the intergalactic medium rise to temperatures of hundreds of thousands or even millions of degrees. Even so, the gas remains extraordinarily thin. It is hot, but not dense. It is heated, but not brilliant. Much of it can only be detected indirectly, through the way it absorbs or emits specific wavelengths of light. This makes intergalactic space an important lesson in scale. The outer universe is not a simple contrast between cold darkness and isolated hot stars. It contains vast stretches of matter that are faint, sparse, and thermally varied. Some zones remain close to the cold background in practical terms. Some are warmed by radiation from distant sources. Some are shock-heated as large structures assemble over billions of years. Yet none of these conditions in this outermost region approach the most extreme temperatures known elsewhere. Intergalactic space sets the stage by showing how much of the cosmos remains restrained. The universe is not mostly fire, it is mostly thinness, distance, and quiet energy spread across unimaginable volume. Radiation plays a steady role here. The microwave background fills all of space and provides the most uniform thermal field in the present cosmos. Starlight and quasar light travel through the intergalactic medium and alter the state of the gas they encounter, over long spans. This radiation helps determine whether hydrogen remains neutral or ionized, whether gas cools efficiently, and whether certain regions stay visible to instruments. But radiation alone does not turn the whole outer universe into a hot place. It passes through most of this realm without being trapped. There are too few particles to hold energy in the concentrated way that dense gas, stellar interiors, or accretion flows can. Intergalactic space receives energy, but it rarely stores it in thick, enduring reservoirs. The calm character of this region also depends on time. The large-scale structure of the universe grows slowly. Galaxies gather into groups and clusters over billions of years. Filaments stretch across distances so great that light itself requires millions of years to cross them. In such a setting, heating often comes from gradual accumulation rather than sudden violence. Gas falls inward under gravity, streams meet, shock fronts form, the matter warms. Yet the process remains spread over enormous scales. This is not the concentrated heat of a stellar core, or the brief flare of an explosion. It is a long, diffuse warming written into the architecture of the cosmic web. Observations indicate that much of the ordinary matter in the present universe may reside in these faint intergalactic structures, rather than inside bright stars and galaxies alone. That conclusion emerges from years of careful study, because this matter is difficult to see directly. It neither shines strongly nor gathers into obvious forms. It reveals itself through absorption lines in the light of distant sources and through delicate X-ray or ultraviolet signatures. This uncertainty in visibility does not mean the matter is unimportant. It means the outer universe hides much of its substance in regions too thin and dim for easy detection. Temperature in such places is not guessed from appearance. It is reconstructed from subtle traces. So the outer calm between galaxies becomes the proper second step in the search for the hottest place. It shows the universe in its restrained state. Here, the thermal story is one of low density, faint radiation, scattered particles, and slow heating on gigantic scales. There are regions of warm and even very hot gas, but they are stretched thin across immensity. They do not dominate by intensity. They remind the observer that heat alone does not define a cosmic environment. Density, duration, structure, and radiation all matter. In the wide spaces between galaxies, the universe remains mostly quiet, and that quiet provides the necessary contrast for everything hotter that lies deeper within the great structures of the cosmos. Far from the thin calm between galaxies, matter begins to gather into the largest bound structures in the present universe. These are galaxy clusters, enormous collections of galaxies held together by gravity and embedded in vast clouds of gas. From the outside, a cluster may seem like a loose arrangement of bright islands suspended in darkness. Yet the galaxies are only the visible markers of something much larger. Most of the ordinary matter in a cluster is not locked inside stars. It fills the space between the galaxies as an extended atmosphere of plasma, a state of matter in which electrons are no longer bound to atomic nuclei. This gas is the first truly immense reservoir of heat in the cosmic journey inward, and it reveals how gravity can warm matter on scales far beyond any single star. The gas inside a cluster is not heated by one simple source. It becomes hot as the cluster forms. Over billions of years, smaller groups of galaxies and streams of matter fall together under gravity. As they converge, their motion is not gentle. Gas plunges inward at enormous speed. When these streams collide, they cannot pass cleanly through one another like beams of light. They crash, compress, and slow. In that slowing, motion is turned into heat. The result is a widespread plasma that often reaches tens of millions of degrees. This is one of the clearest examples in astronomy of gravity acting as a cosmic engine. It does not create energy from nothing. It converts falling motion into thermal energy and stores that energy in a huge volume of gas. At these temperatures, the gas does not shine mainly in visible light. It glows in X-rays. This is why galaxy clusters are among the most important X-ray sources in the sky. Their galaxies may look modest in ordinary telescopes, but the space between those galaxies becomes luminous when viewed in high-energy light. The X-ray glow traces the structure of the hot plasma, showing that the cluster is not empty between its galaxies. It is filled with a vast medium, thin by earthly standards yet dense enough on cosmic scales to hold tremendous heat. In this way, galaxy clusters overturn ordinary intuition. The brightest visible objects are not always the main carriers of energy. In a cluster, the true thermal body lies in the nearly invisible gas spread through the whole structure. This hot plasma does not sit perfectly still. Clusters continue to grow, and many of them bear signs of past collisions. When two clusters or two large subclusters meet, the event is among the most energetic natural processes in the present-day universe. These collisions do not happen quickly on human timescales. They unfold over spans so long that they seem almost frozen when viewed from Earth. Yet the forces involved are immense. Shock fronts move through the gas, heating it further. Turbulence stirs the plasma. Some regions become compressed and brighter in X-rays. Others are stripped away from in falling galaxies and groups, leaving trails of heated gas behind them. The cluster becomes a record of impact written not in broken stone or shattered metal, but in temperature, pressure, and light. Because the gas is so hot, atoms cannot remain whole in the usual sense. Electrons move freely, and the plasma responds not only to gravity, but also to magnetic fields and pressure waves. This creates a medium that behaves differently from ordinary air or water. It can sustain broad waves of compression. It can carry energy across long distances. It can cool in some central regions by radiating X-rays, while in other regions it remains heated by mergers or by energy released from giant black holes in the cluster's central galaxies. Even here, temperature is not uniform. A cluster may contain hotter outer shock regions, cooler dense cores, and disturbed zones where fresh collisions have recently passed through. The heat is immense, but it has structure. Some of the best-known clusters show clearly that heat on this scale is not a matter of simple burning. There is no giant flame in the space between galaxies. There is instead a plasma so hot that its atoms are stripped apart, held within the cluster by gravity and made visible through X-rays. This distinction matters. In everyday language, the hottest place might suggest a compact, dazzling point. In clusters, the heat is diffuse and extended. It occupies regions hundreds of thousands or even millions of light-years across. A person searching only for brightness in visible light would miss it entirely. The cluster teaches that the universe hides some of its greatest heat in volumes too thin to see with ordinary eyes. The central parts of some clusters reveal another important feature. If the gas there is dense enough, it can radiate energy away more efficiently than gas in the outer regions. In principle, this would allow the central plasma to cool and sink inward, forming what astronomers once imagined as steady cooling flows. Observations show a more complicated reality. In many clusters, energy from the central active galaxy, often powered by a supermassive black hole, stirs and reheats the gas. Cavities, ripples, and pressure waves appear in the cluster medium, preventing simple collapse. Even at this stage, the thermal life of the cluster is a balance between cooling and reheating, gravity and feedback, stillness and disturbance. For the search inward, galaxy clusters mark a major step. They are not the hottest environments known, but they are among the largest stable bodies of very hot matter in the present cosmos. Their temperatures can exceed those in ordinary stars at the surface by a wide margin, yet they reach those temperatures through a completely different path. A star is heated by fusion in a dense interior. A cluster is heated by gravitational assembly on enormous scales. One is compact and radiant in visible light. The other is diffuse and radiant in X-rays. The comparison broadens the meaning of cosmic heat and prepares the journey for more concentrated regions where gravity acts more intensely. So this region of the universe, deeper than the calm between galaxies but still vast beyond familiar thought, settles into its own thermal identity. A galaxy cluster is a basin of hot plasma shaped by mergers, compression, and time. It is a place where gravity turns structure formation into heat, and where the space between galaxies becomes more important than the galaxies alone. In this region, the hottest matter is no longer scattered faintly through the cosmic web. It gathers into great reservoirs, luminous in X-rays, restless under collision, and held together by the deepest wells of a large-scale gravity. Within the largest clusters, some galaxies stand out not simply because of their size, but because of what happens at their centers. Deep in these galactic hearts, matter falls towards supermassive black holes. A black hole is a region where gravity becomes so strong that once matter passes a certain boundary, called the event horizon, it cannot return. The black hole itself does not shine. The heat comes from the matter outside it, while that matter is still visible and still moving through space. Gas drawn inward does not usually drop straight down in silence. It circles, collides, compresses, and forms a flattened rotating flow called an accretion disk. In these central regions, the search for the hottest place moves from vast diffuse plasma to a much more concentrated kind of heat, one driven not by cluster-scale assembly, but by the intense gravity of a single compact object. At the outer edges of an active galactic nucleus, the environment may still look calm in a broad image of the host galaxy. Stars shine across the disk. Dust lanes trace spirals or elliptical light. Yet the center can outshine the entire galaxy when enough matter is feeding the black hole. The gas falling inward carries orbital motion. It cannot instantly lose that motion, so it spreads into a disk and gradually spirals closer. As rings of gas at slightly different speeds rub and tug against one another, friction and turbulence convert ordered motion into heat. The process is slow in some places and violent in others. The farther out in the disk, the cooler the gas tends to be. Closer in, the temperature rises sharply. This creates a layered thermal structure, with outer regions glowing in optical and ultraviolet light, and inner regions becoming hot enough to produce X-rays. The heat here differs from the heat in a galaxy cluster. A cluster contains a gigantic volume of thin plasma, heated over long ages by mergers and compression. Near a supermassive black hole, the scale shrinks dramatically, but the energy density rises. Matter is packed into a much smaller region, while moving much faster in a much steeper gravitational field. The gas can reach extraordinary temperatures before crossing the point of no return. This heat is not spread gently through millions of light years. It is concentrated into the central engine of a galaxy. The result is one of the most luminous sustained environments in the known universe, powered not by nuclear fusion as in stars, but by gravitational energy released during accretion. Around many active galactic nuclei there is also dust, arranged in thick structures outside the hottest inner flow. Dust absorbs some of the fierce radiation from the center and re-emits it in infrared light. This means that the galactic heart is not just a point of hard radiation, it is a layered environment of hot gas, ionized clouds, energetic particles, and warmed dust, each occupying a different distance from the central black hole. In some viewing angles, the dust partly hides the inner region, making the nucleus appear as different depending on the line of sight. This does not change the underlying heat. It changes only how that heat is seen from afar. The structure remains one of inward increase, with temperature climbing as matter moves deeper into the gravitational well. Some active galactic nuclei launch powerful jets, narrow streams of particles and energy that shoot outward far beyond the host galaxy. These jets are among the most dramatic signs that the center is not only hot but dynamically extreme. Still, the jet itself is not the main focus of this region. The heart of the matter lies in the accreting gas close to the black hole. Observations show that high-energy radiation from these inner zones can vary over relatively short times, which implies that the emitting region is compact. When brightness changes quickly, astronomers infer that the source cannot be much larger than the distance light travels during that interval. This is one of the clues that the energy is being produced in a small central volume rather than across the whole galaxy. The thermal intensity is concentrated, and the central engine reveals itself through that compact power. The exact temperature in these inner environments is not always simple to define. Different parts of the accretion flow may behave differently. The dense disk has one thermal character: a hotter, thinner corona above the disk. A cloud-like region of energetic particles may produce intense X-rays through scattering processes. In this context, scattering means that lower energy photons gain energy by interacting with very energetic electrons. This can make the emitted light appear harder and more energetic than the disk alone would produce. Observations indicate that such coronae can reach extremely high effective temperatures, though the details remain uncertain because the geometry and particle behavior are difficult to reconstruct from great distances. Science therefore distinguishes between measured radiation and the exact microscopic state of the gas. The region is unquestionably hot. The precise distribution of that heat is still studied with care. Quasars are the brightest examples of this active state. A quasar is an especially luminous active galactic nucleus, visible across enormous cosmic distances. In these objects, the central black hole is feeding efficiently enough that the surrounding disk and related structures radiate with astonishing power. The host galaxy may become almost secondary in appearance, yet the same principle remains in force. The black hole itself is dark. The heat belongs to the matter outside it, in the last visible stages of infall. This is an important correction to ordinary language. The hottest place is not inside the hidden object where no light escapes. It is in the luminous material just beyond that final boundary, where gravity drives motion to extremes and motion is converted into heat. Compared with galaxy clusters, these galactic hearts bring the search inward in both space and intensity. The scale is smaller, the gravity steeper, the radiation harder, and the energy more concentrated. This does not yet settle the question of the single hottest natural setting, because even more extreme short-lived events and earlier cosmic states still lie deeper in the journey. But within the present structure of galaxies, active nuclei represent a major step upward in thermal severity. They show that when matter falls far enough and fast enough, gravity can rival or surpass the heat produced by stars and clusters, turning the center of a galaxy into a furnace of light without flame. So the inner heart of an active galaxy stands as a place where darkness and heat meet closely but do not merge. The black hole remains unseen, while the surrounding matter becomes one of the brightest and hottest sustained environments in the universe. Gas circles, compresses and radiates. Dust absorbs and glows. High-energy light escapes across intergalactic space. The galaxy, which from afar may seem serene, reveals at its center a compact engine powered by descent into gravity. Here, the thermal story has moved decisively inward, from the broad basins of cluster plasma to the concentrated brilliance of matter on the edge of disappearance. Outside the ordered lives of ordinary stars, there are galaxies and regions where stellar change becomes unusually crowded. These are starburst realms, places where stars form at a much higher rate than in quieter galaxies, and where the deaths of massive stars begin to overlap in space and in time. The environment is no longer defined by one calm stellar surface or one isolated galactic nucleus. It is shaped by many young hot stars, many fierce stellar winds, and many supernova explosions unfolding across the same broad region. In such places, heat is not contained in a single object. It fills cavities, streams through superbubbles, and builds a restless medium of hot plasma that can spread far above the galaxy itself. A starburst region begins with gas. Large clouds of cold molecular material gather, collapse, and fragment into clusters of newborn stars. Among these new stars are the most massive kinds, bright blue stars that live briefly and release enormous amounts of ultraviolet light. Their radiation strips electrons from surrounding atoms and creates glowing, ionized regions. At the same time, their stellar winds push outward, carrying fast streams of charged particles into nearby gas. These winds sweep cavities into the surrounding medium and compress gas into shells. Even before any supernova takes place, the region has already become an active thermal landscape, layered with warm ionized gas, hotter shocked wind material, and dust heated by intense starlight. The winds from massive stars matter because they do more than stir the neighborhood. When fast winds collide with slower gas, shock fronts form. Those shocks heat the gas sharply and create plasma at temperatures of millions of degrees. A plasma is matter so hot that electrons and atomic nuclei move separately rather than as intact atoms. In a quiet part of a galaxy, such hot gas may appear only in scattered pockets. In a starburst region, it can become widespread. Many stars contribute at once, and their combined winds merge into larger hot cavities. These cavities may connect with one another until the region becomes filled with overlapping shells, tunnels, and bubbles of high-temperature gas. The visual impression in ordinary light may be one of glowing nebulae and dust, but beneath that softer appearance lies a much harsher thermal environment. Then the first massive stars begin to die. A supernova is the explosive end of certain stars, especially those born with high mass. In a single event, a star throws its outer layers into space at enormous speed. The expanding debris drives a powerful shock into the surrounding medium, heating gas far beyond the temperatures of normal stellar atmospheres. In isolation, one supernova already creates a remarkable hot remnant. In a starburst region, supernovae do not remain isolated for long. One explosion follows another across spans of time short by galactic standards. Their shock waves cross earlier cavities, strike dense clouds, and reinforce the hot plasma already present from stellar winds. The region becomes a layered record of repeated energy release, with each new explosion feeding an existing sea of heat. This repeated input changes the scale of the problem. A single hot star can ionize a local cloud. A single supernova can create a remnant. But dozens or hundreds of massive stars, born in clusters and dying within a relatively narrow interval, can transform the interstellar medium of an entire galactic region. The gas becomes so pressurized that it may break out of the galaxy's disk. When this happens, hot plasma and entrained matter flow upward into the halo in what astronomers call a galactic wind. A wind of this kind is not a breeze in any familiar sense. It is a large-scale outflow powered by the combined effect of stellar radiation, stellar winds, and supernova heating. It carries mass, metals, and energy away from the starburst core and into the surrounding space. The temperature in these starburst-driven outflows can reach millions of degrees, often making them visible in X-rays. This is one of the reasons that some starburst galaxies appear strikingly bright in high-energy observations. The heat does not belong only to the stars themselves. It belongs also to the gas that the stars have disturbed, compressed, ionized, and shocked. In this way, a starburst realm acts as a thermal amplifier. It takes the life cycles of many stars and blends them into one common medium of heating and motion. The result is less concentrated than the immediate surroundings of a supermassive black hole, but more widespread and more chaotic than the heat around ordinary stars. Supernova remnants within these regions also show that heat is not uniform. The forward shock, racing into surrounding gas, can heat that gas to very high temperatures. Behind it lies the shocked stellar debris, rich in heavy elements forged inside the star before the explosion. Dense clumps cool more quickly than thin regions. Magnetic fields shape particle motion. Some energy goes into accelerating cosmic rays, which are very fast-charged particles moving through the remnant and beyond. This means that not all of the released energy stays as heat. Some becomes motion, turbulence, radiation, and non-thermal particles. Even so, the thermal component remains immense, especially when many remnants overlap in the same broad zone. Observations indicate that starburst galaxies can maintain these hot, pressurized environments for extended periods, while active star formation continues. It remains uncertain in detail how efficiently the energy from supernovae couples to the surrounding gas in every case, because dense clouds, magnetic structure, and radiative losses complicate the picture. Even so, the general outcome is clear, where stellar birth and stellar death are densely packed. The interstellar medium becomes hotter, more turbulent, and more expansive than in calmer galaxies. The region no longer behaves like a quiet collection of individual stars. It behaves like a connected engine powered by many short-lived massive stars acting together. In the search for the hottest place, starburst and supernova realms do not yet represent the final extreme. Their temperatures can be very high, and their influence can extend across whole galactic centers and halos, but they still belong to an intermediate scale. They are hotter and more violent than ordinary star-forming clouds, yet less concentrated than the innermost accretion flows around black holes, and far below the conditions associated with the earliest universe, or with the hottest matter produced in particle collisions. Their importance lies in what they teach. Heat in the cosmos can be collective. It can arise not only from one exceptional object, but from many stellar lives overlapping until a whole region becomes transformed. So this inward step brings the thermal story into a crowded and restless domain. Gas collapses into stars. Young stars flood their surroundings with radiation. Winds strike the nearby medium and carve hot cavities. Massive stars explode and drive shocks through gas already disturbed by earlier generations. the heated material rises, expands, and sometimes escapes into a galactic wind. In these realms, the universe shows how repetition can build intensity. One star changes a cloud. Many stars change a galaxy's inner atmosphere. The result is a broad furnace of plasma and motion, sustained by birth and death occurring almost side by side. After the crowded heat of starburst regions and overlapping supernova, the journey inward settles upon stars themselves. A star is a great sphere of hot gas held together by gravity and powered, during most of its life, by fusion in its core. Fusion is the joining of light atomic nuclei into heavier ones, releasing energy in the process. That energy begins deep inside the star and works its way outward until it escapes from the surface as light and heat. The surface is the visible boundary from which most of the star's radiation reaches space. It is this outer layer that gives a star its colour and allows astronomers to estimate its temperature from far away. In this region of the journey, the focus remains only on the surfaces of stars, because even this outer skin already reveals an enormous range of cosmic heat. The first lesson of stellar surfaces is that colour carries temperature. Cooler stars appear red or orange. Stars like the Sun appear yellow-white. Hotter stars appear white or blue-white. This colour difference does not come from paint, flame, or chemistry in the familiar earthly sense. It comes from the distribution of light released by a hot glowing surface. A cooler surface emits more strongly at longer wavelengths. A hotter surface shifts its strongest emission toward shorter wavelengths. Astronomers read this pattern carefully and compare it with models and spectra, which are the separated bands of light showing how much energy appears at different wavelengths. In this way, the colour of a star becomes one of the simplest clues to its surface temperature. Red dwarfs stand at the cooler end of the common stellar range. They are small stars, faint compared with brighter kinds, and their surfaces are much cooler than those of hot blue stars, yet they remain far hotter than anything familiar on Earth. Their light is steady and subdued by stellar standards, and because they use their fuel slowly, they can live for extraordinarily long spans of time. At the surface, they represent a modest kind of stellar heat, still intense in human terms but not close to the highest temperatures found among stars. Their importance lies in contrast. They show that a star can be a true furnace and still be counted among the cooler members of the stellar population. The Sun provides a middle reference. It is a yellow dwarf star, neither among the smallest nor among the hottest. Its visible surface, called the photosphere, radiates at a temperature of roughly several thousand degrees Celsius. The photosphere is not a hard crust. It is a glowing outer layer of gas from which light can escape relatively freely into space. It appears calm from a distance, but close study shows granulation, magnetic activity, and darker sunspots where strong magnetic fields alter the flow of heat. Even so, the general surface temperature remains within the range typical of Sun-like stars. This makes the Sun a useful guide, because it reveals how a familiar star can be powerful enough to sustain a planetary system and still remain far below the hottest stellar surfaces. As stellar mass increases, surface temperature tends to increase as well. Massive stars burn through their fuel more quickly, shine more brightly, and develop hotter surfaces. White and blue stars therefore mark the hotter end of ordinary stellar appearance. Their light is more intense, their radiation more energetic, and their lives much shorter. A hot blue star may have a surface temperature several times greater than that of the Sun. These stars often dominate the light of young clusters and star-forming regions because they are so luminous. even though they are rarer and shorter lived than smaller stars. Their surfaces show that the visible skin of a star can already reach tens of thousands of degrees, making them among the hottest sustained surfaces in the natural universe. Yet even here, an important boundary must be kept clear. Stellar surfaces, however hot, are not the final answer to the search for the hottest place. They're dramatic and easy to picture because they shine directly in visible light, but they are still outer layers. A surface is where energy escapes, not where most of it is generated. This is why the stellar journey must pause here and remain disciplined. The visible face of a star tells much about temperature, mass, and energy output, but it does not yet reveal the deeper heat hidden within. At this stage, only the outer skin matters, and even that skin teaches a useful restraint. What appears most dazzling is not always what is hottest overall. Some stars push surface heat to unusual extremes. Certain stripped stellar remnants and exposed cores can reach far higher surface temperatures than ordinary main-sequence stars. White dwarfs, the compact remains of stars like the Sun after they shed their outer layers, can begin their lives extremely hot at the surface before cooling slowly over time. Some exposed stellar cores associated with planetary nebulae also show very high surface temperatures. These cases demonstrate that a small star-like object can have a hotter surface than a larger ordinary star. Because temperature depends on the state of the exposed matter, not only on size. Still, even these remarkable surfaces belong to the category of outer radiation layers. They are part of the skin of a star or its remnant, not yet the deeper thermal engine. The way astronomers measure these temperatures also matters. A star's color gives a broad estimate, but detailed spectra provide more precision. Absorption lines, which are dark features in a spectrum caused by specific atoms or ions absorbing certain wavelengths, help indicate the conditions in the star's atmosphere. Different lines grow stronger or weaker at different temperatures. By studying them, astronomers infer surface conditions with great care. Rotation, chemical composition, and magnetic effects can complicate the picture, so surface temperature is often expressed as an effective temperature, meaning the temperature of an idealized radiator that would emit the same total energy per unit area. This allows stars of different kinds to be compared in a consistent way. So the surfaces of stars form a clear and necessary stage in the inward journey. They gather the diffuse energy of stellar interiors and release it into space as color and light. Red stars glow more gently. Sun-like stars hold a middle place. Blue stars burn with far greater visible heat. Some compact remnants reveal even hotter exposed surfaces, but the lesson remains steady. These surfaces are not the hottest places in the universe. They are only the outer radiating layers of objects whose deeper regions may be far more intense. In this region, the search pauses on the visible face of stars and learns to separate appearance from depth, brilliance from ultimate heat, and the shining surface from the hidden source below. Beneath the visible surface of a star lies a hidden region where the true thermal engine operates. The surface shines because energy has traveled outward from much deeper layers. Inside, the gas is compressed by the star's own gravity. Pressure rises steadily toward the center. Temperature rises with it. In these inner regions, matter does not behave like the familiar gases of air or steam. It is a dense, ionized plasma under such immense pressure that atomic nuclei move fast enough to overcome part of their electrical repulsion and join together. This joining is fusion, and it is the reason ordinary stars can shine for millions or billions of years. In the journey toward the hottest places in the universe, the interiors of stars mark a major inward step, because here heat is not merely escaping, it is being created and sustained. The outer layers of a star can be thought of as the release zone, but the interior is the working body. Gravity constantly presses inward, trying to compress the star. Heat and pressure from fusion push outward. A star spends most of its life in a balance between these two tendencies. This balance is called hydrostatic equilibrium, meaning that inward pull and outward support remain matched. The concept sounds calm, yet inside the star the conditions are anything but gentle. The central temperature of a star like the Sun rises to many millions of degrees. That heat is necessary because fusion does not happen easily. Atomic nuclei carry positive electric charge, and like charges repel. Only in the deep interior, where temperature and density are high enough, can nuclei come close enough for the strong nuclear force to bind them together. In stars like the Sun, the main process is the conversion of hydrogen into helium. Hydrogen is the simplest element, with a nucleus made of a single proton. Helium has 2 protons and 2 neutrons in its most common form. Through a chain of reactions, 4 hydrogen nuclei are ultimately combined into one helium nucleus, with some mass converted into energy. That energy first appears in the core in forms that include gamma-ray photons and the motion of particles. It then begins an outward journey so slow and complex that the light leaving the surface long afterward no longer resembles its original state. In this sense, the sunlight falling across a planet is the delayed and softened expression of heat created deep within a stellar core. The core is not large compared with the star as a whole, but it dominates the star's thermal life. Only the central region is hot and dense enough for steady fusion in most stars. Outside that core, temperature and density gradually fall, and fusion weakens or stops. Energy then travels outward through the surrounding layers. In some stars, it moves mainly by radiation for a long distance, meaning photons are absorbed and re-emitted over and over as they inch outward. In other layers or other stars, energy is also carried by convection, a process in which hot material rises and cooler material sinks, creating a slow churning motion. These transport mechanisms matter because they shape the star's structure, yet they do not rival the core in heat. The core remains the star's deepest ordinary furnace. As stellar mass increases, the interior becomes more extreme. A more massive star has stronger gravity pressing inward, which raises central pressure and temperature. This allows fusion to proceed more rapidly and through different pathways. In very massive stars, the core temperature becomes far higher than in the Sun, and the rate of energy production rises sharply. These stars live fast and die young because they consume their nuclear fuel at a much greater pace. Their hotter interiors also allow them to fuse heavier elements at later stages of life. What begins as hydrogen fusion can progress to helium fusion, and then to the fusion of increasingly heavier nuclei in the most massive stars. Each stage requires higher temperature and pressure than the one before. This progression reveals an important truth about cosmic heat. A star's surface may be measured in thousands or tens of thousands of degrees, but its interior lives on an entirely different scale. The hidden core can be thousands of times hotter than the glowing skin that appears in the sky. The surface is what escapes. The core is what sustains. This is why stellar interiors matter in the wider search for the hottest place. They teach that visible brightness alone cannot reveal the deepest thermal conditions. The most familiar hot objects in the night sky conceal inner regions far more intense than their calm outer radiance suggests. Still, even stellar interiors have limits. Fusion can support a star only up to a point, and the thermal story changes as fuel is used up. In smaller stars, the core remains comparatively moderate by the standards of the most extreme cosmic environments. In massive stars, the center grows hotter and passes through multiple burning stages, But these stages are temporary and structured. The star does not become infinitely hot. Each stage depends on the balance between gravity, pressure, composition, and energy lost through radiation and neutrinos. A neutrino is a nearly massless particle that interacts very weakly with matter and can escape dense regions carrying energy away. In advanced stars, neutrino losses become important, making the inner thermal balance more delicate and pushing the star toward instability. The layered structure of evolved massive stars becomes one of the clearest examples of inward temperature increase. Hydrogen may still burn in an outer shell while helium burns beneath it, and deeper still, other elements may be fusing in nested shells around the core. Each inner layer tends to be hotter than the one above it. The arrangement resembles an onion in structure, though not in appearance or material. This inward rise in temperature is the natural consequence of gravity compressing matter more strongly toward the center and of each heavier stage of fusion demanding more extreme conditions. By the time a massive star nears the end of its life, its core temperature has risen to astonishing levels, yet even then the star remains a layered body, with each region defined by what can still survive and what can still fuse there. So the inward journey through stars reaches a decisive threshold here. The visible surfaces are left behind, and the deep interiors reveal themselves as sustained nuclear furnaces. Hydrogen is fused into helium. In more massive stars, heavier elements follow in sequence. Pressure and temperature rise inward, and gravity maintains the confinement needed for fusion to proceed. The heat in these cores is immense, far beyond anything felt at a stellar surface, but it is still part of an ordered stellar life. The interior is not yet an explosion, not yet a remnant, and not yet the most extreme matter in the universe. It is the hidden middle of the stellar story, where gravity and fusion hold one another in balance, and where the great quiet light of stars is born from unseen depths. As a massive star approaches the end of its life, the inward layering of its interior becomes more compressed, more urgent, and less stable. The core, once supported by the steady outward push of fusion, now carries the burden of heavier elements and diminishing options. Each stage of burning has already run faster than the one before it. Hydrogen burning lasts the longest. Helium burning is shorter. The later stages become progressively briefer, because heavier fusion yields less energy while demanding higher temperatures. By this point, the star is no longer a calm, long-lived furnace. It is a structure racing through its last available sources of support, with heat and pressure still immense, but no longer enough to guarantee stability for long. In these final stages, the central regions of the star can reach temperatures of billions of degrees. Such heat allows the fusion of heavy elements in the inner shells and core, but the sequence cannot continue forever. Fusion works only while it can release energy. For lighter elements, joining nuclei can produce a more tightly bound nucleus and free energy in the process. But this trend ends near iron. Iron and nearby elements do not provide net energy when fused in the same way. Once the core becomes dominated by iron-rich material, the star reaches a thermal and structural limit. The core may still be extremely hot, but heat alone is no longer enough to reverse the deeper problem. The nuclear path that once supported the star has narrowed to a dead end. At this point, the core is held up mainly by forms of pressure that arise from densely packed matter. One of these is electron degeneracy pressure, a quantum effect that appears when electrons are forced into extremely crowded states. It does not depend on temperature in the same way that ordinary gas pressure does. This helps the core resist compression for a time even when fusion has ceased in the center. Yet the burden above it continues to grow. Shells of fusion outside the core keep producing ash that falls inward, adding mass and increasing compression. The iron core becomes denser and hotter, but this rise in temperature does not restore stable support. The star has moved into a regime where its own success in building heavier elements now works against it. Then the collapse begins. Once the core passes a critical threshold, pressure can no longer balance gravity. The central region falls inward with extraordinary speed. This inward plunge is one of the most dramatic changes in the thermal history of a star. Material that once moves in slow equilibrium now races inward under the force of gravity. Electrons are squeezed into protons, producing neutrons and neutrinos. The matter becomes increasingly neutron-rich and incredibly dense. The infall is so rapid that the core shrinks from a stellar scale to something far smaller in a very short time. During this collapse, temperature and density both soar. The star has crossed from a phase of sustained fusion into a phase of catastrophic compression. The neutrinos released in these conditions matter greatly. A neutrino is a very light particle that interacts so weakly with matter that it can often escape dense regions carrying energy away. In the final collapse, immense numbers of neutrinos are produced. For a brief time, they dominate the energy flow. They stream outward from the collapsing core, and although most pass through the star with little interaction, a fraction deposit energy in the surrounding material. This effect is one of the key parts of modern understanding of core collapse supernovae. Observations and models indicate that neutrinos help revive the stalled shock and contribute to driving the explosion, though the full details remain complex and are still being refined. When the collapsing inner core reaches nuclear density, meaning a density similar to that found inside atomic nuclei, it becomes much harder to compress further. The inward fall halts abruptly in the central region. The core rebounds slightly, and a shock wave forms at the boundary between the halted inner core and the still infalling outer layers. This shock begins to move outward through the star. At first, it is powerful, but it loses energy as it tears apart heavy nuclei and pushes through dense matter. For a moment, the explosion is not yet secure. The shock weakens. Then the intense neutrino flow from the newborn compact core transfers some energy to the surrounding region, helping the shock regain strength. When that outward-moving shock finally succeeds, the star's outer layers are blasted into space. Here the thermal conditions become extreme in a different way from the steady heat of stellar interiors. The core collapse and shock passage produce brief temperatures far above those of ordinary stellar burning. Matter behind the shock is heated violently. Nuclei are broken apart and reassembled. Heavy elements are formed under rapid energetic conditions. The heat is not now part of a long balanced life. It is part of a short, violent transition from star to remnant. This is one of the first regions in the inward journey where the question of a hottest place becomes tied not to a stable object, but to a fleeting event. The temperature may rise enormously, but only for a brief interval and in a rapidly changing environment. The explosion does not erase all structure at once. Different layers of the star respond differently depending on their composition, density, and distance from the center. Some material is launched outward at great speed. Some may fall back. The exact outcome depends on the mass of the original star and the details of the collapse. What remains at the center is usually a neutron star, though in some cases continued collapse can form a black hole. Yet in this section, the focus remains only on the final moments of the massive star itself. This is the transition point where the ordered thermal engine fails, gravity takes control, and the highest temperatures of the star's life are reached during collapse and explosion. So the end of a massive star is not merely a fading, It is a thermal escalation driven by loss support, rising compression, and catastrophic inward motion. The core becomes iron-rich and unstable. Gravity overwhelms pressure. Collapse drives temperature and density upward with astonishing speed. Neutrinos pour out. A shock forms and, if revived successfully, races outward through the star. In this brief terminal interval, the star reaches conditions far beyond those of its ordinary interior, not because it has found a stronger, steady source of power, but because its structure has failed. Heat here is the companion of collapse, the signature of matter being pushed past the limits of stable stellar life. After the explosion of a massive star, the heat does not vanish with the first outward blast. It remains in the expanding debris and in the gas that surrounds it. A supernova remnant is the long-lived aftermath of the explosion, a growing structure made of shocked stellar material and shocked interstellar gas. It is not a single flash, but an evolving thermal system. In this stage, the star itself is gone as a stable body. Yet the heat released in its death continues to shape space for thousands of years. The remnant becomes a fast-moving shell, and the search inward now follows the shock front that carries the memory of the explosion into the surrounding medium. At first, the debris from the supernova expands rapidly into space that may already have been altered by the star's earlier winds. The outer edge of that debris forms a forward shock, which is a powerful disturbance that plows into the surrounding gas and heats it suddenly. Behind it, a reverse shock moves back inward through the ejected stellar material, heating that material as well. This creates a layered structure. One hot region is made from the gas that had already existed around the star. Another hot region is made from the star's own expelled matter. Between them lies a contact surface where the two kinds of material meet but do not instantly mix. The remnant therefore becomes a thermal archive, with different zones preserving different histories of the star and its surroundings. The temperatures reached in these shocked regions are immense. Gas behind the forward shock can be heated to millions of degrees or more, enough to produce strong X-rays. The reverse shocked ejector can also become extremely hot, especially in young remnants where the expanding material is still moving at enormous speed. At these temperatures, atoms are stripped of many or all of their electrons, and the remnant shines in high-energy light, yet this heat is not evenly distributed. The remnant grows into a textured object, with filaments, knots, shells, and clumps. Dense regions cool more quickly. Thin regions stay hotter for longer. Magnetic fields and turbulence distort the flow. Heat in a remnant is therefore dynamic and structured, never still and never perfectly smooth. This stage also reveals that temperature and brightness do not always match simple expectation. Some parts of a remnant glow brightly in optical light because gas there is cooled enough for certain atoms to emit visible radiation. Other parts remain too hot for that and appear chiefly in X-rays. Radio emission can trace accelerated electrons spiraling through magnetic fields. This means a remnant must be read across many wavelengths. No single band tells the whole thermal story. The visible filaments may appear dramatic, but some of the hottest regions are better seen in X-ray observations, where the full force of the shock heating becomes clear. As the remnant expands, it sweeps up more and more interstellar material. This changes the balance of the system. Early on, the motion is dominated by the original stellar ejector. Later, the mass of swept-up gas becomes comparable to or greater than the mass that was expelled by the star. At that point, the remnant enters a stage where the surrounding medium matters greatly in determining its structure and temperature. The forward shock continues to heat new gas, but the expansion gradually slows. Energy spreads into a larger volume. Radiative cooling becomes more important in denser regions. The remnant is still hot, but it is no longer simply the outward rush of stellar debris. It has become a broader interaction between the explosion and the galaxy around it. Some remnants reveal particularly complex thermal behavior because the surrounding medium is uneven. A shock traveling into a dense cloud behaves differently from one moving into thin gas. In dense material, the shock may slow and the gas may cool relatively quickly, producing bright optical emission. In thinner material, the shock can remain fast and hot, producing more persistent X-rays. This gives many remnants an irregular appearance. One side may be brighter or cooler than another. One region may show rich chemical signatures from the exploded star, while another is dominated by heated interstellar gas. The remnant is shaped not only by the explosion itself, but also by the landscape into which it expands. The hot plasma inside a remnant also carries the products of stellar history. Heavy elements forged inside the star before the explosion are flung outward and then heated by shocks. Their spectral lines allow astronomers to identify oxygen, silicon, sulfur, iron, and other elements in the remnant. These lines are more than labels. They show where the ejected layers have gone, how strongly they have been shocked, and how the explosion redistributed the material of the star into the wider galaxy. In this sense, the remnant is both a thermal structure and a chemical one. It is hot because of violent motion, and it is revealing because that heat makes the expelled matter visible in detail. Not all of the energy in a remnant remains as heat. Some is used to accelerate cosmic rays, which are extremely fast-charged particles. Supernova remnants are considered important sites for this acceleration. As particles cross the shock front repeatedly, they can gain energy and reach speeds close to the speed of light. This process removes part of the available energy from the thermal gas. It also changes the shock structure itself. The remnant is therefore not just a glowing hot shell. It is a system where heat, magnetic fields, turbulence, and particle acceleration all compete for the energy released in the original explosion. Over time, the remnant cools and merges into the interstellar medium. Its sharp boundaries soften, its hottest zones fade. The energy it once held as intense thermal motion is dispersed into the surrounding galaxy, but for a significant span, the remnant remains one of the clearest examples of long-lasting shock-heated matter in the universe. It is less concentrated than the instant of core collapse that created it, yet it preserves that violence in a more extended and observable form. The heat is no longer hidden deep in a star or compressed into a compact core. It has spread outward into a great shell, where astronomy can watch the aftermath unfold. So the supernova remnant stands as the heated remains of stellar death, a broad and evolving structure in which shock fronts continue the thermal story long after the first explosion. The forward shock heats the surrounding gas. The reverse shock heats the ejected matter. Filaments, clumps, and shells record differences in density and motion. X-rays reveal plasma at millions of degrees. Heavy elements glow through the heat that now carries them outward. In this region, the universe shows how a brief extreme event leaves behind a long afterlife of temperature, motion, and light, turning the remains of a destroyed star into a lasting monument of shock-heated plasma. What remains at the center after a core collapse supernova is often a neutron star, an object so dense that the ordinary language of matter begins to fail. A neutron star forms when the inner core of a massive star collapses until most of its matter is packed into a body only a small distance across by stellar standards, yet containing more mass than the Sun. The name reflects the dominant role of neutrons in this crushed matter. Electrons and protons have been forced together in the collapse, leaving a compact remnant supported by the pressure of matter under nuclear conditions. In the inward journey toward the hottest place, the neutron star marks a turn from expanding shock-heated remains to a far smaller region where density becomes as important as temperature and where the meaning of heat changes under immense compression. A newborn neutron star is extraordinarily hot. In the immediate aftermath of collapse, its interior temperature can rise to vast values, far beyond the surface temperatures of ordinary stars and beyond the hot gas in most supernova remnants. Yet this heat is trapped inside matter of such density that energy does not flow outward in the same way it does in a normal star. The remnant is compact, opaque, and crowded with particles under extreme pressure. Neutrinos again play a leading role. In the first moments and minutes after birth, the young neutron star loses a great amount of its thermal energy through neutrino emission. These nearly non-interacting particles escape far more easily than light can, carrying energy away from deep inside and allowing the object to cool rapidly compared with ordinary stars. The earliest thermal life of a neutron star is therefore not governed mainly by surface radiation, but by hidden energy loss from the interior. This makes a neutron star a different sort of hot object. In an ordinary star, the surface shines steadily because energy from fusion diffuses outward over long times. In a neutron star, the initial heat is a leftover of collapse and compression, not the product of a stable central fusion engine. The object begins its life hot because gravity has crushed matter into a new state. Its temperature then declines as neutrinos and later photons remove energy. The heat is real, but it belongs to a remnant rather than to a living star. The thermal story is one of aftermath, not continuation. The interior of a neutron star is not simple. Near the outer layers there is a crust made of nuclei and electrons arranged under extraordinary pressure. Deeper down, neutrons dominate, though protons, electrons, and possibly more exotic particles may also be present depending on the density. Observations indicate that the exact composition of the deepest core remains uncertain. It is known that matter there exceeds the density of atomic nuclei, but it remains uncertain whether the innermost region contains only densely packed neutrons and a small admixture of other particles, or whether more exotic states of matter appear. This uncertainty matters because it affects how heat moves, how the star cools, and how pressure supports the remnant against further collapse. At the surface, a young neutron star can still be extremely hot, often radiating strongly in X-rays. Yet even here, the surface is not comparable to the visible photosphere of a normal star. It is a thin outer layer above a body of immense gravity and density. The gravity at the surface is so strong that it bends the path of light and affects the behavior of the atmosphere resting above the solid or semi-solid outer crust. This atmosphere may be only a very thin layer by ordinary standards, yet it shapes the escaping radiation and influences how astronomers infer the star's temperature. This surface temperature may be measured in millions of degrees in a young neutron star, but the deeper interior begins far hotter still and cools along a different path than any normal stellar body. Magnetic fields complicate this picture further. Many neutron stars possess magnetic fields vastly stronger than those of ordinary stars. In some cases, especially in magnetars, the magnetic field is so intense that it can influence the crust, channel charged particles, and power bursts of high-energy radiation. A magnetar is a neutron star whose extreme magnetic field becomes a major source of its activity. In such objects, heat is not only a leftover from formation, it can also be sustained or redistributed by magnetic decay and crustal stress. The star may produce energetic outbursts, and its surface may show localized hot regions rather than a perfectly uniform thermal glow. This means the thermal life of neutron stars is not identical from one object to another. Age, magnetic field strength, composition, and spin all shape how the remnant cools and radiates. Rotation also matters. A newborn neutron star can spin rapidly, sometimes many times each second. This rapid spin stores rotational energy, and in pulsars some of that energy powers beams of radiation and particle winds. A pulsar is a rotating neutron star whose beams sweep across space and can be detected as regular pulses if they cross Earth's line of sight. In these cases, not all the remnant's energy budget remains thermal. Some becomes electromagnetic emission, particle acceleration, and interaction with surrounding space. Even so, the underlying thermal state remains important, especially in the early life of the star. The cooling curve of a neutron star, meaning the way its temperature declines with age, is one of the main tools astronomers use to infer what is happening inside matter at these crushing densities. This makes neutron stars a bridge between known matter and uncertain matter. They are hot, but their significance lies as much in compression as in temperature. A galaxy cluster teaches how gravity heats diffuse gas on vast scales. An accretion disk near a black hole teaches how gravity concentrates energy into a small luminous region. A neutron star teaches what happens when gravity crushes stellar matter itself into a compact remnant so dense that ordinary atomic structure cannot survive. The temperature is immense, especially at birth, but it exists within a body whose defining quality is density. Heat here is inseparable from matter under pressure beyond anything achievable in ordinary astrophysical objects short of black holes and the most violent transient events. So the neutron star marks an inward stage where the search for the hottest place becomes more subtle. The object is born with extraordinary internal heat, but it also cools rapidly through neutrinos. Its surface can remain at millions of degrees, while the interior evolves under uncertain nuclear physics. Strong magnetic fields and rapid rotation may alter the way heat emerges or is redistributed. The remnant is no longer a star in equilibrium, nor an expanding shell of debris, but a compact body of crushed matter carrying the thermal memory of collapse. In this region, the universe shows that heat can survive not only in fire-like radiation or in shocked gas, but also in matter compressed to nuclear density, where temperature, gravity, and the nature of matter itself become tightly bound together. Closer still to the deepest gravitational wells in the universe, matter takes on another thermal form. Around black holes, gas does not always fall inward as a cold stream. When enough matter is present and carries angular momentum, it settles into a rotating accretion disk. Angular momentum is the tendency of a moving body to continue rotating unless something changes that motion. Because of this, gas cannot simply drop straight into the black hole. It must lose orbital energy and redistribute momentum before it can move inward. In that process, the disk heats dramatically. The accretion disk is therefore one of the clearest examples of gravity being converted into thermal energy in a compact region. Here, the search for the hottest place enters a domain where matter shines fiercely, not because it is making energy through fusion, but because it is descending into extreme gravity. A black hole itself does not radiate like a hot surface. The defining boundary of the black hole, the event horizon, marks the limit beyond which light cannot escape. The heat belongs instead to the visible matter outside that boundary. Gas in the disk moves at enormous speed. Inner parts orbit faster than outer parts, and this difference in motion creates shear, meaning adjacent layers slide past one another. Magnetic turbulence and internal friction allow energy and angular momentum to be transferred outward while mass moves inward. As that happens, orbital energy is converted into heat. The farther inward the gas travels, the more energy it can release. This is why the inner disk becomes the hottest part of the flow and why accretion can be so efficient as an energy source. The temperature in an accretion disk depends strongly on the mass of the black hole and on how rapidly matter is falling inward. Around stellar mass black holes, which form from the collapse of massive stars, the inner disk can become hot enough to emit strongly in X-rays. Around supermassive black holes, the inner disks are much larger, and their main emission often peaks in ultraviolet or optical light, though hot surrounding regions can still generate X-rays. This difference in emitted light does not mean the larger systems are unimportant thermally. It reflects how size changes the balance of temperature and radiation. A smaller disk around a smaller black hole can reach higher characteristic temperatures in its inner visible flow, while a larger disk spreads energy over a greater area. In both cases, the central principle remains the same. Gravity drives inward motion, and inward motion becomes heat. The disk is not the whole story. Above and around it there may be a corona, a region of much hotter, thinner plasma populated by extremely energetic electrons. The word corona here refers not to a planetary or solar feature, but to a hot extended zone associated with the accretion flow. Photons from the disk can pass through this region and gain energy by scattering off those electrons, emerging as X-rays. This makes the corona a major source of high-energy radiation in many accreting black hole systems. Observations indicate that the corona can reach extraordinary effective temperatures, though its exact shape and behavior remain uncertain. It may be compact and close to the black hole, or more extended in some systems. It may change rapidly as the disk changes. The heat here is harder to picture than the hot gas of a cluster or the glowing surface of a star. It belongs to a turbulent, magnetized environment where radiation and particles interact intensely. Near the innermost stable orbit of the disk, the conditions become especially severe. There comes a point where circular motion is no longer stable, and gas begins a rapid final plunge inward. Before reaching that point, however, the matter has already been heated by repeated internal interactions. The disk can radiate a large fraction of the gravitational energy released before the gas disappears. This makes black hole accretion one of the most efficient natural engines in the cosmos. A star powered by fusion converts only a small fraction of its mass into energy over its lifetime. An accretion disk can release a much larger fraction of the infalling mass energy as radiation before the matter is lost beyond the horizon. This does not mean every black hole system is always bright or hot. Many black holes accrete little and remain dim. But when the flow is active, the thermal intensity can be immense. The radiation from the inner disk and corona also shapes the surrounding environment. Nearby gas may be ionized by the outgoing high-energy light. Winds can be driven from the disk surface, carrying material outward even while other gas moves inward. In some cases, powerful jets form along the black hole's rotational axis, though the detailed origin of jets involves magnetic fields and rotation as much as simple heat. Within the disk itself, the balance between heating and cooling determines the state of the flow. If matter radiates energy efficiently, the disk remains relatively thin and bright. If it cannot radiate efficiently, the flow may puff up into a hotter and more diffuse structure. This means there is not one single accretion disk model for all black holes. There are several thermal regimes, each set by how quickly mass arrives, how strongly fields stir the gas, and how efficiently energy escapes. Observations of black hole binaries in the Milky Way, where a stellar mass black hole feeds on gas from a companion star, have been especially valuable because these systems can change state on humanly observable timescales. They brighten, dim, harden, and soften in X-rays as the accretion flow reorganizes itself. Such changes show that the inner thermal structure is not fixed. It responds to the rate of inflow and to the geometry of the disk and corona. Supermassive black holes in active galactic nuclei evolve more slowly, but the same broad physics applies. Across these different scales, the disk becomes a natural furnace created by gravity and sustained by continual inflow. In the wider search for the hottest place, accretion disks around black holes occupy a special position. They are not as brief as the first moments of a supernova collapse, and they're not as universally hot as the earliest phases of the cosmos. Yet they are among the hottest long-lived natural environments that can be observed directly through their radiation. They show how matter can reach extraordinary temperatures without fusion and without the need for a solid surface. Their heat is born from descent, from loss of orbital energy, and from the compression and turbulence of gas forced to spiral inward. So this inward region settles into a sharp thermal identity. Around the black hole, the disk glows because moving gas is ground down by gravity into radiation. The inner disk becomes hotter than the outer disk. A corona of even more energetic plasma may hang above it, scattering light into the X-ray range. The system is layered, unstable, and efficient. No flame is present, and no surface burns in any ordinary sense. Instead, heat arises from matter nearing disappearance while still visible, still colliding, and still able to radiate. In this region, the universe reveals one of its most powerful sustained ways of making hot matter, not through nuclear burning, but through the last luminous stages of infall. Beyond the sustained heat of accretion disks lies a class of events in which thermal and energetic extremes appear in brief, concentrated outflows. These are the domains of relativistic jets and gamma-ray bursts. A relativistic jet is a narrow stream of matter and energy moving at a speed close to the speed of light. A gamma-ray burst is an intense flash of gamma radiation, the most energetic form of light, released during a catastrophic event such as the collapse of a massive star or the merger of compact remnants. In this region of the inward journey, heat is no longer defined mainly by steady structures like stars, clusters, or long-lived disks. It appears in violent channels and brief eruptions, where matter is accelerated, shocked, and compressed so intensely that ordinary thermal language begins to blur into the language of extreme energy. Jets can form around accreting black holes when magnetic fields thread the rotating flow and help launch material outward along the axis of rotation. They may extend far beyond the central engine, sometimes across distances larger than the host galaxy. Yet the thermal story of a jet is not simple. Much of its energy is carried as directed motion, magnetic structure, and fast particles rather than as ordinary heat alone. A jet is therefore not merely a hot pipe of glowing gas. It is a highly organized outflow in which energy remains concentrated and channeled. Still, internal collisions, shocks, and interactions with surrounding matter can convert part of that directed energy into heat and radiation. The hottest regions are often not the smooth body of the jet itself, but the places where faster material overtakes slower material, or where the outflow slams into the medium around it. These shocks matter because they create localized zones of extreme conditions. When jet material crashes into surrounding gas, the kinetic energy of bulk motion is transformed into disordered motion, radiation, and particle acceleration. The gas can be heated to enormous temperatures. electrons can be driven to energies high enough to produce X-rays and gamma rays. Yet even here, science distinguishes carefully between thermal temperature and the broader energy of highly accelerated particles. Some of the most dramatic light from jets is non-thermal, meaning it does not arise from ordinary hot matter radiating as a warm body, but from fast-charged particles spiraling in magnetic fields or scattering photons to higher energies. This means the search for the hottest place enters a region where heat remains important. But where temperature is no longer the only useful measure of extremity, gamma-ray bursts sharpen this difficulty. They are among the most luminous transient events known in the universe. For a brief span, a gamma-ray burst can release more energy and high-energy light than a galaxy emits across many wavelengths during the same interval. Long gamma-ray bursts are associated with the collapse of very massive stars into black holes, while short gamma-ray bursts are linked to mergers involving neutron stars and, in some cases, black holes. In both cases, a compact central engine forms and powers narrow, ultra-fast jets. If one of these jets is pointed toward Earth, the burst appears exceptionally bright. The observed radiation comes from a small region, moving outward at tremendous speed, under conditions of extreme compression and shock. Within the earliest stages of a gamma-ray burst outflow, temperatures can become extraordinarily high. The newly launched jet begins in a dense and energetic state, with photons, particles, and magnetic fields packed into a small volume. As it expands, some of its energy is converted from internal energy into outward motion. Deeper within the flow, before full expansion, the thermal component can be immense. Observations indicate that part of the burst emission may arise from a photosphere, a region where the outflow becomes transparent enough for trapped radiation to escape. The word photosphere here means the visible release layer of the jet, not the surface of a star. Below that layer, radiation and matter remain strongly coupled. Above it, light escapes more freely into space. The temperature associated with the deepest visible stages of this outflow can be far beyond the heat of ordinary stellar matter. Still, these conditions are brief and elusive. A gamma-ray burst does not linger as a stable hot environment. It erupts, expands, and fades. The prompt flash is followed by an afterglow across X-rays, visible light, and radio waves as the jet interacts with its surroundings. That afterglow can last much longer, but it reflects a cooling and broadening structure rather than the initial deepest extreme. This brevity matters for the larger question. A present-day galaxy cluster can remain hot over immense timescales. An accretion disk can stay hot while matter continues to fall inward. A gamma-ray burst reaches higher transient conditions, but only in a narrow outflow, and only for a very short interval. The hottest matter here is tied to a moment of violent release, rather than to a sustained cosmic environment. The same is true in a broader sense for the jets of active galactic nuclei and other compact systems. Their inner launching regions may host plasma of astonishing effective temperature and energy density, especially in association with hot coronae and strong magnetic fields. But the jet itself carries much of its power outward as motion. Along the way, shocks and reconnection, a process in which magnetic field lines rearrange and release energy, create patches of intense heating and radiation. These patches may flare and fade. They may brighten rapidly and then subside. The thermal structure is therefore uneven, intermittent, and embedded in a flow whose defining quality is speed. It is heat carried within directed escape. In the inward search, these brief extremes hold an important place because they show how high temperature can arise when collapse or merger creates a compact engine and then releases energy through narrow channels. The relevant scale is no longer the size of a star, a cluster, or even a whole accretion disk. It is the thickness of a jet, the depth of a launching zone, or the compressed region of a shock within an ultra-fast outflow. The temperatures reached can exceed those in many more familiar hot environments, but they are hard to isolate cleanly because radiation, particle acceleration, magnetic energy, and bulk motion are all tangled together. Science can state with confidence that these are among the most extreme present-day natural conditions. It remains uncertain in detail how temperature should be assigned in every part of such flows, because not all particles and photons share energy in a simple equilibrium. So this region narrows the question further. Jets and gamma-ray bursts do not merely produce brightness. They reveal brief episodes in which matter and radiation are driven to extraordinary intensity in small, fast, and highly organized outflows. Shocks heat the gas. Particles are accelerated. Radiation escapes from layers that were once trapped deeper within the flow. The hottest conditions are transient and difficult to compare directly with stable reservoirs of hot plasma. Yet their importance is clear. They show that the path toward the true hottest place does not lead only through larger objects or denser remnants. It also passes through brief, violent flashes, where the universe concentrates energy into narrow beams and allows some of its fiercest thermal states to appear for only an instant before they expand, cool, and vanish into the dark. To move further inward now requires change in direction. Space itself must be followed backward through time. The hottest natural places in the present universe, whether in accretion disks, jets, or collapsing stars, are local and temporary. The early universe is different. It is not a hot object inside a colder background. It is a time when nearly all of space is hot at once. In this region of the journey, the setting is no longer a galaxy, a star, or a remnant. It is the young cosmos itself, filled everywhere with dense plasma and radiation. The search for the hottest place therefore passes from isolated structures into a universal state, where heat is not confined to one region, but belongs to the whole visible cosmos at an early stage of its history. In the first several 100,000 years after the Big Bang, ordinary atoms do not yet exist in stable form across the universe. Space is filled instead with a hot plasma of free electrons, atomic nuclei, and photons. A photon is a particle of light. In this dense early environment, photons do not travel freely for long distances. They scatter constantly from the charged particles around them, especially from electrons. Matter and radiation are therefore tightly linked. The universe is bright in every direction, but not transparent. Light is present everywhere, yet it cannot move cleanly across space because it is repeatedly interrupted by interactions with the plasma. The young cosmos resembles neither the dark modern sky nor the interior of a star, though it shares features with both. It is luminous, dense, and thoroughly hot. This plasma is mostly hydrogen nuclei, which are single protons, along with helium nuclei and free electrons. Small traces of other light nuclei are present as well, left from the first minutes of cosmic nuclear formation. But the dominant condition is one of ionization. Ionization means that electrons are not bound to atomic nuclei. In later cosmic ages, neutral atoms can form and allow light to travel long distances without frequent scattering. In this earlier phase, that has not yet happened. The heat is high enough to keep matter in a charged state, and the density is high enough to keep radiation trapped in repeated contact with it. The temperature is not merely high in one violent pocket. It is high throughout the whole observable region of the young universe. As the universe expands, this plasma cools. Expansion stretches space itself, and with that stretching, the average energy of radiation decreases. Matter also thins out. The cooling is gradual on cosmic terms, but decisive. Eventually, the temperature falls enough for electrons to combine with nuclei and form neutral atoms, mainly hydrogen and helium. When this happens, the universe becomes transparent for the first time on large scales. Photons that had been scattered again and again can now travel much more freely. The ancient light released at that transition still fills the cosmos today as the cosmic microwave background. Cooled by expansion to only a little above absolute zero, that faint background is the cold remnant of a once much hotter universal plasma. This early plasma phase is important because it reveals that the thermal history of the cosmos is not only a matter of where heat is now, but of when heat once was everywhere. In the present universe, the hottest places are isolated against a largely cold background. In the young universe, there is not yet such a contrast. Temperature differences exist, but they are small compared with the general fact that all of space is hot, dense, and filled with interacting radiation and matter. The plasma carries sound waves, pressure patterns, and tiny density variations that later grow into galaxies and clusters. These variations are delicate, but the overall environment is far more uniform than the modern cosmos. The heat is widespread and foundational. It belongs to the whole medium out of which later structures will emerge. The temperature during this plasma era is far above anything found at the surface of stars and beyond the sustained temperatures of many large present-day structures. Yet it is still cooler than the even earlier conditions that precede it. This section therefore remains disciplined and stays within the era of the universal plasma as a bounded region of the inward path. Here, atoms are absent, radiation is trapped, and the thermal state of the cosmos is defined by continuous interaction between photons and charged matter. The significance lies not only in the absolute temperature, but in the way that temperature fills all space. The universe is not merely hosting hot objects, it is itself in a hot phase. Observations strongly support this picture. The cosmic microwave background preserves the cooled imprint of the era when light last scattered from matter. Its spectrum, which describes how the radiation is distributed across wavelengths, is extraordinarily close to that of an ideal thermal source. This is one of the clearest signs that the early universe passes through a phase of near thermal equilibrium, meaning that matter and radiation exchange energy so efficiently that they share a common temperature. Small departures from perfect uniformity are present, and those departures are essential for later structure formation, but the overall thermal character is clear. The young cosmos is a nearly uniform plasma bath whose present cooled afterglow can still be measured with remarkable precision. The plasma era also teaches something deeper about the meaning of place. In ordinary speech, a place suggests a bounded location surrounded by something different, but the early universe blurs that distinction. The hottest place, at this stage, is not a local chamber of fire or a hidden core within an object. It is the state of cosmic space itself at an earlier time. The inward path therefore becomes a path through layers of physical history. Outer and inner no longer mean only far and near in space. They also mean later and earlier in time, moving from the cooler, expanded cosmos inward toward denser and hotter beginnings. This follows the same rule of one region at a time, but the region is now temporal rather than geographic. So the young universe in its plasma phase stands as a vast and luminous thermal sea. Free electrons, light nuclei, and trapped photons fill every direction. Radiation and matter remain coupled. The whole observable cosmos glows, though not transparently. Expansion steadily lowers the temperature until neutral atoms can form, and ancient light can travel outward into the future. In this region, the search for the hottest place leaves behind the scattered furnaces of the modern universe and enters a time when heat is universal, shared by all space, and written into the very background from which every later star, galaxy, and cluster will eventually arise. Before the young universe becomes a plasma of free electrons, nuclei, and trapped light, it exists in an even more compressed and energetic state. To move inward to this region is to move into the first fractions of a second after the Big Bang, when temperature and density rise far beyond the later plasma era. The cosmos is still expanding rapidly, but it is much smaller, much denser, and much hotter than it will be only moments afterward. Ordinary atomic nuclei have not yet taken shape. Atoms are impossible. Even protons and neutrons are not yet permanent features throughout the whole medium in the earliest part of this interval. The thermal story now approaches the point where matter is no longer arranged in the forms familiar from stars, gas clouds, or even the later early universe. It enters a regime governed by the fundamental constituents of matter and radiation in a far more direct way. In these first fractions of a second, energy is the ruling condition. Space is filled with an intense bath of particles and radiation, all packed together so closely and interacting so frequently that they share a common thermal life. The distinctions that later matter to astronomy, such as the difference between a star and the space around it, do not yet apply. There are no stars, no galaxies, no planets, and no stable atoms. There is only the early cosmic medium, so hot and dense that the building blocks of later matter exist in a much freer and more energetic state. Expansion has already begun, and as space expands the temperature falls, but at this stage the fall is from a level so high that even the later universal plasma seems comparatively calm. The first fractions of a second are understood through the combined work of cosmology and particle physics. Cosmology describes how the universe expands and cools as a whole. Particle physics describes the behavior of the smallest known constituents of matter and the forces acting among them. Together they show that as the young universe cools, different kinds of particles become more or less important, and different transitions become possible. At very high temperature, matter and radiation remain in rapid exchange. Particles are constantly created and destroyed in collisions. The cosmic medium behaves less like a collection of distinct objects and more like a unified thermal bath, with the contents determined by the available energy. As the temperature declines through this era, the universe passes through important thresholds. Quarks, which are fundamental constituents of protons and neutrons, and gluons, which carry the strong nuclear force between quarks, do not remain permanently confined inside individual protons and neutrons at the highest temperatures. Instead, matter exists in a freer state. Later, as expansion continues and the temperature falls, quarks become bound into hadrons, a family of particles that includes protons and neutrons. This transition is one of the most important thermal changes in the early cosmos. It marks the passage from a more elementary and less confined state of matter to one closer to the substance from which later nuclei and atoms will be built. During this interval, other key events also unfold. Matter and antimatter interact intensely. Antimatter is composed of partners to ordinary particles, with opposite charge but similar mass. When matter and antimatter meet, they can destroy one another and convert their mass into radiation. In the early universe, both are present in abundance. Observations indicate that a slight excess of matter over antimatter eventually remains, though the exact origin of this imbalance is still not fully understood. What is clear is that as the universe cools, most matter-antimatter pairs annihilate, leaving behind the small surplus of matter that later forms galaxies, stars, planets, and living beings. This process belongs to the thermal history because it depends on the changing balance between creation, annihilation, and expansion in an intensely hot background. Neutrinos also play a significant part in this epoch. In the earlier and hotter part of the interval, they interact often enough to remain in thermal contact with the rest of the cosmic medium. As the universe expands and thins, there comes a time when they decouple, meaning they stop interacting frequently and begin to travel more freely through space. This is another example of how the inward path through time is also a path through changing thermal relationships. At first, nearly everything is tightly coupled. Later, as cooling proceeds, different components separate in their behavior. Radiation, neutrinos, quarks, and other particles no longer all share the same level of direct interaction. The temperatures in this era exceed anything associated with present-day stars, accretion disks, or supernova remnants. They also exceed the temperatures of the later photon-baryon plasma, the stage where light and ordinary charged matter remain coupled before atoms form. The whole universe is hotter, denser, and more uniform than at any later time described so far in the journey. Yet even here, careful language remains necessary. Science can describe this era with strong confidence back to very early times. But the confidence is not limitless. The general picture of expansion, cooling, particle interactions, and early thermal transitions is well supported. It becomes less certain only when attention moves even closer to the absolute beginning, where current theories of gravity and quantum physics are not yet fully united. This makes the first fractions of a second a boundary region between what is strongly described and what remains incomplete. The universe is known to have passed through states of extraordinary temperature and density. It is known to have cooled through a series of fundamental transitions. It is known that the matter now seen in stars and galaxies emerges from this early thermal history. But the earliest conceivable instant, where a complete theory of quantum gravity would be required, remains beyond present confirmed description. That limit does not weaken the reality of this region. It simply means that science distinguishes clearly between what observations and established theory support and what still lies beyond secure reach. So this inward step arrives at a cosmos hotter than any later structure, not because one object has become extreme, but because the whole universe is still close to its densest known beginnings. Matter has not settled into nuclei, atoms, or stars. Particle species are abundant, interactive, and governed by the immense shared energy of the early medium. Quarks and gluons are not yet confined in the later ordinary way. Matter and antimatter are still engaged in mutual destruction, leaving behind the slight excess that will shape all later structure. Neutrinos remain coupled and then begin to separate. The universe here is not a landscape with hot regions. It is itself a nearly all-encompassing furnace of fundamental particles, cooling rapidly as it expands, and carrying within that cooling the first clear steps from raw energy toward the material cosmos that will follow. At the deepest confirmed thermal layer reached by modern science, matter enters a state that no longer resembles atoms, stellar gas, or even the crushed matter of neutron stars. This state is called quark-gluon plasma. A quark is a fundamental constituent of protons and neutrons. A gluon is the particle that carries the strong nuclear force, the force that binds quarks together inside those larger particles. Under ordinary conditions, quarks and gluons are confined. They do not move freely over distances larger than the tiny scale of the particles they inhabit. In quark-gluon plasma, that confinement breaks down. Matter becomes a dense, hot medium in which quarks and gluons move in a more collective and less bound way. In the search for the true hottest place in the universe, this state is crucial because it represents the hottest matter that science has directly produced and measured. This is not a natural place in the ordinary astronomical sense. It is not a region in a galaxy or the heart of a long-lived star. It is a recreated condition, made briefly in heavy ion collisions inside particle accelerators. Heavy ions are the nuclei of heavy atoms, such as lead or gold, stripped of their electrons and accelerated to speeds close to the speed of the light. When two such nuclei collide head-on, the energy density in the tiny overlap region becomes immense. The collision does not simply shatter the nuclei into separate fragments. For a brief instant, it creates a droplet of matter so hot and dense that protons and neutrons melt into their more elementary constituents. This is quark-gluon plasma, a laboratory glimpse of conditions that fill the early universe in its first tiny fractions of a second. The temperatures reached in this state rise to trillions of degrees Celsius. That scale stands far above the temperatures of stellar cores, supernova remnants, galaxy clusters, and the visible parts of accretion flows. Even many extreme present-day natural events are discussed with more uncertainty than this laboratory result, because in the accelerator, the state is inferred through controlled experiments repeated many times. The plasma exists for only a minute fraction of a second and occupies an exceedingly small volume, but it is not guessed at loosely. It is reconstructed through detailed measurements of the particles streaming outward after the collision, through their collective motion, through the suppression of certain particle states, and through other signatures that show matter has passed through a deconfined and thermalized phase. Thermalized here means that the produced matter behaves as a connected medium sharing energy in a common way, rather than as a mere spray of unrelated fragments. One of the most striking discoveries about quark-gluon plasma is that it does not behave like a thin gas of free particles. Instead, observations indicate that it flows more like an almost perfect liquid, with extremely low viscosity. Viscosity is a measure of internal resistance to flow. Water has lower viscosity than honey. In this plasma, despite the immense heat, the collective behavior is remarkably fluid. This surprises ordinary intuition. One might expect the hottest matter to be the most disordered and gas-like, yet the quark-gluon plasma created in colliders shows strong collective flow, suggesting that even under these extreme conditions the matter interacts intensely and moves as a coordinated medium. Heat here does not produce simple chaos. It produces a new state with its own coherence. The comparison with the early universe is important, but must be handled carefully. In the first fractions of a second after the Big Bang, the entire universe passes through conditions where quarks and gluons are not confined inside hadrons. In the laboratory, only a microscopic droplet of comparable matter is produced. The laboratory plasma is therefore not the whole early universe in miniature. It is a tiny sample of one important phase of early cosmic history. Still, the comparison is scientifically powerful. By creating this plasma, experiments allow the properties of that ancient state to be studied in ways impossible through astronomy alone. The hottest confirmed matter is therefore both a present laboratory achievement and a window into the hottest confirmed phase of the young cosmos. This brings the question of the hottest place to its most precise answer. If the question asks for the hottest matter ever directly measured by science, quark-gluon plasma is the answer. If the question asks for the hottest natural state known to have existed in the universe, then the corresponding early universe phase of deconfined quarks and gluons reaches that same category on a cosmic scale. This does not mean every version of the question is settled identically. Certain present-day transient astrophysical events may involve conditions that are difficult to compare directly, because they mix temperature, particle acceleration, radiation, and bulk motion in ways not fully reducible to one simple number. But for confirmed thermal matter, produced, analysed, and understood within established physics, quark-gluon plasma provides the firmest peak. The methods used to infer this state are careful and indirect, as they must be. No instrument is placed inside the plasma itself. The droplet forms and vanishes too quickly. Instead, detectors surround the collision point and record the thousands of particles that emerge afterward, from their distribution, momentum, correlations, and suppression patterns. Physicists reconstruct the properties of the short-lived medium that existed before freeze-out, the moment when the expanding matter becomes too cool and dilute to remain in the same collective state. What matters here is that the evidence converges. Different observables support the same picture of an extremely hot, dense, deconfined medium with strong collective flow. The claim rests not on one dramatic number alone, but on a whole architecture of consistent results. There is a final calmness in this answer. After the journey through cold intergalactic space, cluster plasma, galactic hearts, stars, collapse, remnants, neutron stars, black hole disks, jets, and the early plasma cosmos, the deepest confirmed heat is found not in a vast glowing object visible in the sky, but in a tiny fleeting state of matter produced under controlled conditions. The true hottest place is not a place in the ordinary sense. It is a physical state, reached when matter is driven beyond the boundaries of ordinary nuclear structure. In that state, the universe reveals something more basic than stars or galaxies. It reveals what matter does when heat becomes so extreme that the familiar building blocks of protons and neutrons can no longer hold themselves apart from the deeper sea of quarks and gluons within. So the inward path comes to rest at the hottest confirmed matter known. Quark-gluon plasma exists only briefly, only in a minute region, and yet it stands above all earlier stages in measured thermal intensity. It is both a laboratory creation and a recovered memory of the young universe. It answers the question not with a landscape of fire, but with a state of matter beyond ordinary form, where confinement dissolves, collective flow emerges, and temperature rises to the highest level science has securely recreated. Here, the search reaches its innermost confirmed region, and the meaning of heat becomes inseparable from the most fundamental known structure of matter itself. The journey now grows quiet. The hottest place has turned out not to be a blazing star, nor a bright galaxy, nor even the fierce rim of a black hole alone. It has narrowed gradually from the cold background of the cosmos through larger and hotter structures, then inward through stars and their endings, then backward through time into the young universe, and finally into a fleeting state of matter more basic than any familiar object. The path has shown that heat in the universe is layered. Some heat fills vast regions thinly, some is hidden beneath visible surfaces, some appears in collapse, in shock, or in violent outflow. Some belongs not to lasting places, but to moments. At the deepest level confirmed by experiment, heat becomes a condition in which the ordinary boundaries of matter dissolve, and yet the wider cosmos remains mostly cold. The ancient background still drifts through all directions. Galaxies still float in darkness. Stars continue their long, quiet shining. Even the hottest known matter exists only briefly before cooling, expanding, and passing into other forms. This gives the story a certain stillness. Extreme heat is real, but it does not dominate the universe forever. It appears, transforms matter, and fades. The great cosmic silence remains around it. In that silence, the hottest known state becomes part of a larger order, one phase among many in a universe that carries both deep cold and unimaginable heat within the same unfolding whole.